In physics, we have a lot of concepts, right? So these concepts, a lot of time is we observe and we define. We first have to define what is it, and then we can decide how we're going to use it, right? So same thing with torque. So how do we define torque? First, we define torque is the turning effect of a force around a pivot point. And the symbol is T with a hook. So that's a Greek letter for torque. And then a unit is going to be Newton meter. Okay, so now beforewards, when we talk about force, we always talk about a force pusher object. So it's what we call a linear motion. So what the word linear means, it just means it's going to move in a straight line. It's either accelerate or decelerate, so it's moving in that direction of force. Okay, but when we have torque, we are starting to encounter something called a rotational motion. Okay, so what is the example of a torque? Let's have a look over here. So, for example, if I have this handle over here, right? So if I'm applying a force, this force did not make the thing just simply accelerate. Rather, it's actually making this thing start to rotate. And this force has a turning effect. But in order for it to have this turning effect, it has to have a pivot point. So this is going to be the pivot point. To have a pivot point, and then you will be able to make the thing to turn. Does it make sense? Okay, so let's use another example. Another example is typically we have something as a spanner. So let's say we have a spanner. We have a spanner over here. So this is where the, what do you call it, the nut is, right? Okay, and then when you push it, you gave a force over here. Now this force is not going to make the object fall down. Rather, it's going to make the object start turning because there is a pivot point over here. Does it make sense? So torque just describes how much of this turning effect you can have. The bigger the torque, the easier you turn. If the torque is small, it's very hard to turn. Does it make sense? Okay, so that's what torque is. Okay, so another typical example of this will be a seesaw situation. Say if you have a seesaw, so the middle over here is going to be where the pivot point is. And so if you have a person standing over here, now this person have a weight force, and this gravity force or weight force push this thing, it's going to make it rotate, right, along this pivot point. So in order for it to not rotate, what do you need to do? Have a think. If you're the person standing over here, now you're going to start to fall down and rotate this way, right? So what can you do to make it not rotate?
The ground.
Oh yeah, you can have a ground over here supporting it, or if you are another person, you're trying to make it balance, you can stand on this side over here. Now, if you stand over here, now it's going to have a torque going in this opposite direction, so now they can be balanced. Does that make sense? Okay, sweet. So now we're going to investigate more about this. But first, let's say, well, how do we calculate torque? So torque calculation, you use this equation. Torque equals to force times distance. The unit torque is Newton meter, and force is Newton, and d is distance. But this distance is not any distance, and rather we call it the perpendicular distance from the pivot point to the force. Okay, so I want you to write this down. And then later we're going to encounter situations where you need to get the perpendicular distance, and we'll see what does it actually mean. Okay, so we're going to use the spanner as an example to check out our equation, see if this equation makes sense. Okay, let's have a look over here. If you have a really big force, are you going to make it have more turning effect, make it turn easier or turn harder? If you have a big force. Easier, right? Yeah, if you have a big force, you will have a big torque, turning effect, right? Okay, if the distance from the pivot point to your force is very, very long, say if you have a thing like this long, is it going to be very easy to turn or harder to turn? If they're very long it's very easy to turn, right? If you're a very short one, you think about it, if you're only this short, you're trying to rotate this thing, it's very hard, right? So we actually use this all the time, okay? So it's harder to turn. So where do we use this? We actually use it everywhere. Let's just say, let me just look at the scissors. Okay, this is an interesting design scissor. That's because this scissor got quite a long side over here and a long side over here, right? So when you cut something, where do you put the thing? Say if you want to cut something quite hard, do you put it over here or do you put it very close over here? Yeah, you put it very close over here, right? And your hand moves very far away. So if your hand is moved very far away, you got a lot of, we call it lever. You got a lot of lever over here. The so-called lever is just a perpendicular distance. So when you cut things, say I cut a piece of paper over here, then it's very easy for me to cut, right? But if I put my hand over here to push it, that will be very hard to push because the distance is too short. Then I don't have a lot of rotational turning effect. Does it make sense? So my torque will be small. So that is why the longer it is, you can think, the easier to cut. That's why when I cut my tree, I actually did some housework this weekend. When I cut my tree, I got that thing. And then it was super long, like this long. I go cut. Where the front to cut the tree, only this big to cut, right? So then I got a lot of turning effects going that way, okay? So you can see you have to do two things, force and distance. Okay, so force and distance. Now, the unit is, force is Newton, and that is meter, so Newton times meter is Newton meter, right? Okay, so that's the torque. And, okay, so, and torque has two directions. So if we have a look, And the pivot point is a fixed point. This point is fixed over here. Let's say we got a seesaw over here. I'm going to use this eraser to be the person. So what direction is this torque going to be acting? So if you put the thing on the right side, what kind of direction is it going to rotate? It's going to rotate clockwise. Yeah. So this one, FG1, will have a clockwise torque. I'll first say here is clockwise. And anti-clockwise. So this one, FG1, will have a clockwise torque. I'll say not us. I wouldn't say will have. It has, right? Because it's already tried to turn it. I can call it torque clockwise, or torque 1, or whatever you call it, okay? Because this is F1. Okay. And I'll say here FG2 as an anti-clockwise. Torque. Yeah.
What's the thing after the symbol?
After what?
The symbol of torque.
Oh, this is torque. It's torque. Torque clockwise, torque anti-clockwise. Yes. I'm going to label this one the pivot point in the middle over here as well. Okay, so which one is clockwise, which one is anti-clockwise, and you have to decide, and it depends on where the pivot point is, right? So what you can do, a trick that I teach the student to use, if you get confused, what you do is you hold your pen at the pivot point, and then you use your hand to rotate it, oh yeah? So that's clockwise, right? Or you hold the pivot point, you use the force, give the force, oh, that's going anti-clockwise. If you're not too sure, have a look at your watch, then you will be able to see it, okay? Sometimes it can be very confusing because pivot point not always in the middle. Sometimes the pivot point could be on the side. Does that make sense? Okay, sometime I'll give you guys some questions a bit later, okay? All right, so now we have another important concept. It's called equilibrium. Okay. Okay, so what is equilibrium? Equilibrium, there are two criteria for something to become equilibrium. The first criteria is when all the forces are balanced. Or we can say net force is 0. That means all forces can be cancelled. What happens when all forces are balanced? There's no linear acceleration, right? It's either stationary or it could be moving at a constant speed. And I say, well, because of this, the action is there is no linear acceleration. Okay, and then number two is not only the forces need to be balanced, and the turning effect of these forces will need to be balanced as well. Otherwise, it's not equilibrium. It will start rotate. Does it make sense? Okay, so I say here when all the torque are balanced. So clockwise torque, another way of writing it is say clockwise torque will equals to anti-clockwise torque. And then the result of that is there is no rotational acceleration. Yeah.
So if it's rotating at a constant speed, that means it's reached equilibrium.
It's actually still equilibrium, yeah. Just like how you're traveling at a constant speed, yeah, that's still equilibrium. Okay, so the question, sometimes they just ask you this: what is equilibrium? And that's it. You just have to achieve merit. And you also have to write this, the effect of these two criteria. Okay? And another way of testing you is this. They say, oh, the object is under equilibrium. Then they ask you to calculate the force or whatsoever. And then you know, well, if the force is under equilibrium, you need to know, okay, I've got to use the force, how they're balanced. And I've got to use how the torque is balanced, the situation to calculate it and do the question. Does it make sense? Okay, so now I'll give you guys a few situations. And say this. Why does equilibrium need to match these two criteria? Okay, let's think of this situation. If you have a box over here, right? And you can have a 5 Newton force acting in this direction. And then say 5 Newton force acting in this direction. Now let's have a think. Is this going to be equilibrium or not?
No.
So why would this not be equilibrium?
This will be rotational acceleration.
Yeah, very good. Because the force is balanced, 5 Newton going down, 5 Newton going up. So this object is not going to fly up or fly downwards because the vertical forces are balanced, right? But you can see the torque is not balanced because this one, by the way, sometimes like where the pivot point is, you can decide. Because pivot point is just something we use to analyze, okay? I can say, let's say this is the middle point. Normally the center mass is going to be the pivot point. So let's say, what kind of direction is this torque? This is clockwise. What about this one? Yeah, also clockwise. And you can see these two are helping this object rotating, right? So there is a rotational connection. So this situation is not equilibrium. This is not under equilibrium. Because it matches the first criteria, but it does not match the second criteria. Yeah.
So it must be both. It can't be.
It must be both. I say F net equal to 0, and then but torque clockwise does not equal to torque anti-clockwise. So it matches this criteria, but it doesn't match the second criteria. So that's not equilibrium. Okay, in order for us to match equilibrium, say this. This is example A. Let me give it example B. So example B is, it still has the same block, and this time, my force is going to push over here, 5 Newton, and I have a force also pushing over here at 5 Newton. Okay, let's say this object is floating in space, there's no gravity. Okay, we're analyzing this object floating in space. Well, now let's have a look. We can set the, again, this one, the force is going to be balanced, right? I'm going to say the net force equal to 0. And then let's have a look at the torque. So I put this point, still center mass, as the pivot point. So what kind of torque does this force give it, the top one? That's anti-clockwise, yeah. That's the anti-clockwise torque. What about this one? That's a clockwise, because it's making going that direction, right? Okay, and this is 5 Newton, that's 5 Newton, and the distance is the same. So now these two torque is gonna equal to each other and balance. So now, torque clockwise equal to torque anti-clockwise. So this object is at equilibrium. Because of these two reasons. Does that make sense? Okay, so this is the ideas of torque. What is torque? And what is equilibrium? And how does they work together? So in your book, it has two parts about equilibrium. One they call linear equilibrium. So you don't need to take it out. Just when they say linear equilibrium, they just mean the forces are balanced. You don't need to think about torque. Okay, but the one about rotational equilibrium on your page 5, and that's when you need to use torque to calculate questions. Does it make sense? So basically, all the questions we've done before, we say, oh, the box sitting on a slope, not moving, and that is actually at equilibrium because it's not moving and it's not rotating. But all you actually need to do is just use the force, the first one, the net force is 0 to calculate it. But the more difficult questions where equilibrium, you might need to use both of these criteria. Or sometimes you only need to use the second one. You just need to figure out the torque is balanced. Then you can figure out the answer. Does it make sense? The difficult question is you need to use both these things, okay, which we will have a look together, okay. All right, so that is the teaching for the concepts over here. So we're going to move